All right, so let's get going. So, see, Deb Deep will be here on Friday. So, we're all going to transition out. Then I'm back Monday and Wednesday. Then he's back on Friday. Then who knows? It's just ping pong ball here. So I hope you don't get too bounced around. So on Monday we kind of derived the Gaussian beam. We didn't really derive, but we went through and developed this process. Let me just write it down again. We found the electric field as a function of position, both radial and z, had this form and had a whole bunch of terms. So omega naught 1 plus z over z naught squared. We had an e to the minus r squared over omega squared of z. An e to the minus j k r squared over 2r of z. E to the minus j kz minus tan inverse of z over z naught. So this is what we found when we went through and found the envelope function for the beam. We got this big expression here. We introduced a whole bunch of terms. So we have omega naught. That's the size of the beam waist. And I'll draw a picture in a minute. And we had omega of z. That's the size of the waist everywhere. And that went as omega naught times 1 plus z over z naught squared to the 1/2. We had z naught, which is the confocal parameter. That was pi omega naught squared over lambda. I'll talk about what happens when if we're in an index or a fraction, you always just take lambda and divide by n. So if we have an index or fraction b, it would be n pi omega naught over lambda. But we'll talk about that later. So index or fraction I've not discussed, but we'll include that. We had a r of z, the radius of curvature of the beam. And that had a formula of z times 1 plus z over z naught. I think that's wrong. 1 z naught over z, yeah. Squared. And then, of course, we had q. And we had this parameter q, which was just z plus j z naught. And I think that's most of the terms we went through in the q parameter. And then we noticed that q has this form, but if we invert it, 1 over q was equal to 1 over the radius of curvature minus j lambda over pi times omega of z squared. So q is a very, very powerful number. And then let's draw a picture of the mode. We had this. Here's our optic axis. So let's say the z-axis. The field does something like this. If we look at the cross section of the beam. So here's z. And when it comes to a waist, that's z equals 0. So the minimum spot of the beam is the beam waist. It's got a radius of omega naught. So a diameter of 2 omega naught at z equals 0. And the wavefront is planar at this point. So if we look at the radius of curvature, it's a plane wave here. And then as we start to move away, it starts to pick up some curvature according to that formula r of z. So this shape is defined by that r of z. And we noted that the curvature is flat here. If you go to infinity, it's flat, it's planar. And so it reaches some sort of maximum curvature along in here. And the place where it's the most curved is a distance z naught away. And that's where your curvature is equal to 2z naught. So here r equals infinity. It goes to 2z naught and then approaches infinity again. And that's at z naught. And also at z naught, the size of the beam is the square root of 2 omega naught. So omega of z naught. So that's where the area doubles. So we did all of that on Monday. Just lots of parameters here. And it's just, we introduced all these terms which describe a beam. Now, we didn't talk much about the longitudinal phase factor. Let me just mention that, and then we'll move on. So the longitudinal phase factor introduced this term here. So when we solved that, that introduced that. And this, of course, just simply describes how, as the beam gets bigger, the intensity of the electric field has to decrease. So it's just kind of the 1/r of field spreading. But it also introduced this term here. And what that represents is there's a little bit of phase shift. Let me take a plane wave cruising along. And it just goes along and it accumulates phase kz. And every one of these is half wavelength apart. Versus a focused beam, a Gaussian beam, if they're right in phase here, what happens is this accumulates just a little bit more phase than the other one. And so when I get out here far enough, I'm going to find that there's about a 1/4 lambda. There's pi/2 phase shift between this and where the curved beam is. And likewise this way. So this is going to be about, pi/2 lagging. And so what's happening, there's a little more phase accumulated as this wave goes from -infinity to infinity than a plane wave, because it has to go just a little bit further due to this focusing. So that's all it is. So mainly here in the focus, you pick up a lot of phase. When you're, when you're in the, where is that stupid term? There, tangent of z naught. When you're between 0 and z naught, you're going to pick up pi/4. And then after you've gone about 5 or 6 z naughts, you basically have covered most of it, because the tangent of 20 is the same as tangent of infinity almost. So most of this phase difference is accumulating right in this zone here. So that's all that is. And it's a very minor, subtle thing. It's going to affect the resonant frequency of a laser, but just slightly, just a fixed offset, nothing major. We rarely think about that term, but that's what it's all about. Okay, so now we've got all this stuff here, and a lot of questions come up. Okay, where did this come from? How do we take advantage of this? How do we set where z equals 0 is? How do we choose omega naught? How do we do all these things? So today we're going to show you how to do that. And it's just, I love this. It's just it's the best part of lasers altogether. So we went through all this stuff, and we derived Q. I'll say Q of z. And Q of z is what's going to be our tool we use a lot. So Q of z is just simply z plus jz naught. But as I pointed out, if you know this tells you how far you are from the waist. This tells you how big the waist is. So you know everything you need to know. So Q of z is a very rich parameter and tells us everything we need to know. And so we're going to use that. And it came out of this differential equation. The second thing we did, we used ray tracing to develop these ABCD matrices. These are not rays, these are waves. This is Maxwell's equations coming to a solution. This was Snell's law. That's all we did. We got those two things. Today we're going to combine them. And this is just you've heard of Schrodinger's equation and you've heard of Maxwell's equation, but the biggest of them all is the ABCD law. And if I could have the Star Spangled Banner go off right now, I would. It's an awesome equation. So we're going to look at what's called the ABCD law. And this is how we connect all of this stuff to reality. So the ABCD law, it's real simple. Q, oops, I can't even write. I'm so excited I can't even write it. Q2 equals A Q1 plus B over C Q1 plus D. That's the ABCD law. So we take the components of the matrix and we just literally use them, and they tell us what Q is after the fact. So I've got some beam. Who knows what it is? I got some beam. It's cruising along. And you tell me, oh, right here, Q equals some value. Call it Q1. Now I take this, and I put a lens here, and I go some distance L, and I put another lens, and then I go another distance L2, and I put yet another lens, and I go another distance, and I finally get to this point here. So I'm going to go from here to here, and I want to know what the beam looks like here. What's the beam look like here? It's going to go through lenses and propagate and refract and all kind of junk. So what's it look like? Well, it's real simple. I just compute the ABCD matrix connecting this point to that point. So I'm going to have a matrix of a lens, a propagation, a lens, you know, a bunch of these things, stack them together. At the end of the day, I will have an ABCD which relates this, and out will be my new lens. And it's that simple. I don't care what you put in here. If you can describe that as an ABCD, you can figure out how the mode went from here to there. That's how powerful it is. Now, and what's amazing is it has no right to exist, does it? This is ray tracing. This is wave equation. And somehow we blend them together. It's such a moment we have to celebrate. So I brought something to celebrate. I hope you don't mind. So we have little donuts with flags in them. So you have to come down and get a flag. So everybody come down, grab one. Because this is just, this is bigger than Schrodinger. And grab your, I only have a few napkins. If I could have martial music going, I would. Versions of the ABCD law, we can take, oh, God, I erased it. We've got Q1, Q2 equals AQ1 plus B over CQ1 plus D, or we have 1 over Q2, and I don't want to get it wrong here, is, okay, yeah, there we go. C plus D over Q1 over A plus B over Q1. Sometimes I want to know Q, you know, Z plus Z naught. Sometimes I want to 1 over Q, which is 1 over the radius and 1 over the spot size. So we'll use both independently. But these are the big guys. We're going to use these constantly in laser design. And honestly, they do have a reason to exist, but it's hard to imagine. Here's a few. There's a token napkin here too if someone needs them. Okay. Anyway, so let's do some examples. So let's try some real trivial stuff just to demonstrate. Let's say I've got a beam cruising along, and I'm here at some point Z1, and I know what Q1 is. My beam is cruising along. I'm going to let it propagate a distance L. So I'm going to go L, and I wonder what is Q2. Now, this is a pretty stupid problem because I know Q1 is just, it's Z1 plus JZ naught. If I just let it propagate and nothing else happens, I'm pretty sure I could say this is just going to equal to Z1 plus L plus JZ naught, right? All I've done is I've just changed it. I'm just further away from the waist. But if I apply the ABCD law, let's just see how that works. So the ABCD for propagation is 1L01. So Q2 equals 1 times Q1 plus 0 plus L divided by what I got, C times Q1. What am I doing? C is 0. Okay, 0 plus 1. So this equals Q1 plus L, and that's exactly what I got. Okay, so that was a pretty stupid, simple example. But it does demonstrate at least that it, you know, we always test it, see if it works. What gets more interesting is, say, going through a lens. So let's say we go through a lens. So got some beam cruising along, doing its thing. I put a lens here. I'd like to know what happens to the beam after I go through that lens. So I have to describe the beam here as Q1, whatever it's going to be. And I have to choose a focal length. Let's see. Well, I got a good example here. Let's try this. Let's say I've got Z naught here. Here's Z equals 0. And Z naught equals, well, let's say omega naught equals 1 millimeter. Lambda equals 1 micron. There's Z equals 0. I'm going to go 100 centimeters. I'm going to hit a lens. I'm going to let the lens be 50 millimeters, 50 centimeter focal length. And I want to know what happens to the beam. So I've got a waist. It's cruising along. Hits a lens. It's going to focus. Let's see what happens. So how would I compute this? Well, I have to figure out Q1 right here. So Q1 is going to be Z naught plus 100. Z naught is just pi omega naught squared over lambda. I know omega naught, I know lambda, I know pi. This works out to be, you can do the numbers yourself. I got 100 pi. And the units are centimeters. So if you do it in millimeters or whatever, just pick a unit. You can do it in meters. I don't care. I got in big trouble once. I always do my calculations in centimeters. And I was doing some cavity design and coming up with stuff. And I have a commercial code by this German fellow. And I was getting a different answer for my spot size by 3.16. And I looked at the formula and there's a pi. Sometimes pi is there, not. And I said, oh, the guy forgot pi. So I write him an email, say, you know, sir, you know, I've been doing this a long time. My design differs from yours, and I think you forgot to put pi in there. And I get this very German, my equation is correct. You know. And so I go through again, I check. No. I said, no, you're off by pi. I keep with this 3.16 number. And you know, he said, I take this from this book. You know, it is true. You know, you are wrong. You know, and oh God, you know. And then I keep messing around, and I finally realized what happened. He was using millimeters, and I was using centimeters, and the square root of 10 is 3.16. And so he was right. And it was just a unit thing, you know. And so I wrote him on, thank you. Felt dumb. So 3.16. I just thought it was pi, you know. So just pick your unit and go with it. And so I use centimeters typically. I don't know why, but I think Germans use millimeters. A lot of you use meters. That's fine. Whatever you want to use. So here's Z naught. So what's Q1? Q1 equals distance from the lens for the waist. That's 100 plus J Z naught. Okay, so that's Q right there. That totally describes my beam. Now I'm going to go through that lens, and I'd like to know what it looks like here. So I use the ABCD law. And ABCD for a lens, we all know and love. 1, 0, minus 1 over F. 1. So again, I'm units of 50. So what's Q2? Okay, Q2 equals A Q1. So it's going to equal 100 plus J 100 pi plus B divided by C times Q1. So it's going to be minus 1 over 50 times 100 plus J 100 pi plus 1. There's my new Q. Now here's where you start, you know, doing your complex numbers, simplifying it. Here's where I make my mistakes. So I almost religiously just switch to Mathematica at this point, just let it do it. But you know, it's easy to do. You gotta, what I want to do is convert this into a real and an imaginary term so I can get it in terms of my usual Q. So you just convert this into the real and imaginary. So I'll spare you the math, but you go through and do that. And what I got by doing that was this is equal to minus 51.23 plus 7.76 J. So there's the new Q. Now, what does that tell you? Okay, I now know what's going to happen. I know it's going to come to a focus in 51.23 centimeters. Z is negative, so that means if this is 0, I'm over here, I'm heading toward it. So, kind of makes sense. What that says is this beam is going to be going down like this. If that's 100, this is 50. So it's going to be coming in like this, and it's going to reach a minimum right here, and that distance is 51.23 centimeters from that lens. Does that make sense? So Q immediately tells me where the waist is. How big is the waist? How tight's the focus? Well, the new focus is right here. This is the new Z equals 0 now. So this is the old waist. As soon as I transform it, I've put a new waist out here, so I've got a new 0. And my new 0 is here. And the size of the beam is going to be, I know pi omega naught squared over lambda equals Z naught, 7.76. And so I know lambda, I know pi, I know that, solve for omega naught, and I find that omega naught, the new beam waist, is going to be 157 microns. So, as soon as I do this transform, I not only know where the new waist is, I know how big it is. So now I know how to transform this beam. And let's say I really wanted to focus at 75 or something like that. I could go through and adjust my focal length or move this around. I can adjust my situation now to put the focus where I want it and the size I need. So I've got that ability. So I can compute now how to transform this into anything I want by if I know my end goal, I know my starting point, I just have to put the ABCD between it, and I got it. So that's how powerful this thing is. So now we can just transform these things all over the place. So that's a very nice thing. It's interesting. Well, maybe not that interesting. One example I thought of, when we talk about lenses. Remember I said, okay, I hand you a lens. How do you figure out what the focal length is? How do you do it?
Measure the front of the object and see when it focuses.
Yeah. You take parallel rays and see where they come in. So you look at the sun or a distant lamp or something. What happens if we take a laser beam? And let's say I've got a laser beam, and I've got it fairly big, and I'll bring it in, and we'll put it right here at the focus, so it's plane waves. So the rays are all literally parallel at this point. Let's make it a big beam. I'll put a lens here, and I want to see where it focuses. Does it focus at the focal point? And so it's pretty easy to do. Here, Q1 just equals J Z naught. So it's a very simple one. I've got this lens here. So I do the same thing. And I'd like to figure out where does it come to a focus? And of course, how big is it? And so you do the same thing, and you find that Q2, it's going to come down here. Here's Q2. So Q2, just initially you get something gross like, J Z naught minus 0 or plus 0 divided by minus 1 over F J Z naught plus 1. And you got to get that into real and imaginary. And when I did this, I got the real part becomes, oh God. Oh yeah, okay, here's the real part. Minus Z naught squared F over F squared plus Z naught squared. That's pretty gross. It's not F. It's not F. And in fact, it's a little bit less than F if you put the numbers in. So what you're going to find that when you focus a beam with a laser, and say, okay, I'll take my sunlight's going to focus a distance, F away from the lens. In this situation here, it's going to come to a focus, and here's F, and you focus always a little bit before it. So this beam comes in and it focuses before we actually hit the focal point. What's going on there? This is diffraction. So the beam, rays just come in and they just keep on going. They're going to cross. So rays are just going to zip in, and they're going to hit that all together. But a laser beam, it's coming down, it's starting to diffract, and so it's always spreading. It's always spreading. So it starts spreading out, and so it hits its minimum before F. This is already starting to spread out a bit. So it's always just a little bit shy of your focal point. And you can just show that. Now we'll go through the math. We plug some numbers in, you'll see how that works. Okay, so that's how we can take a laser beam and put it anywhere you want. You want to make a CD reader, you got a laser diode, you got a disc, you got to get that beam over here focused down to a certain spot. You're going to put a series of lenses and stuff, and you're going to compute exactly where to put that and how to do it. This is an amazingly powerful tool for taking a laser beam and putting it anywhere you want. And that's how you do it. It will always work. But Yeah, question.
Wait, so that quantity over there, minus z dot squared f, or
Yeah.
f squared, what exactly is that? Is that q2?
This is the real part. This is the real part. So this is this distance. This is z. This is the distance. I'm sitting here. This is how far I am from the focus.
Okay.
It's a negative number. It means the focus is ahead of me.
Okay.
And it's a real number. So that would tell me how far I have to go till I hit the waist.
To hit the waist.
The waist, yeah.
So the focal point is farther away from
Yeah.
the waist.
This is less than f.
Okay.
Yeah.
But I thought focal point is where the beams all focus towards, right?
That's what we say, but in fact, it's not the case. So the focal point is, using Snell's law, if I have Snell's law and rays, they will cross, at that point. Now, if I make my beam huge, if I make Z naught gigantic, then Z naught squared just completely blows that away, and then my focal point is in fact F. And Snell's law deals with physically large beams. So when we start getting down, diffraction occurs when your beam is small, and the closer it gets to lambda, the more diffraction effects kick in. So in the extreme, where I have a big beam, so I have a Z naught might be 10 to the 8th meters or something like that. Yeah, you're going to find that it focuses right at the focal point. But as that beam gets smaller, it doesn't. Yeah.
Thank you.
So, okay, well that's fun. And you will find this useful when you're building your laser. I'm going to give you a laser on the table, and you're going to build your system over here, and you've got to get that beam from here to there and get it in the right spot. So you got to put some lenses and stuff in the position to get that beam over here and get it the way you want it. You can't just shove the laser beam in. You've got to manage it. So how do you get that beam from here to here? A, B, C, D. Just okay. I got that. I want this. I'll put a lens there. Yeah, that is. So use it for transporting beams, getting them around. But the real power comes in designing a cavity. So what you want to do now is, I want to generate this stupid beam. I don't want to just take it. I want to be the master of the beam. I want to make it. So how do you make these things? So that's the cavity design. So now let's apply the ABCD law to cavities. So remember how we took a cavity and we did a round trip ABCD. You're wondering, why are we doing that? Well, we figured out stability and that kind of nonsense. But it's really much richer than that. So I have some cavity. We'll make just a simple generic cavity. I started at some point. I did a round trip, and I got the ABCD for that round trip. And then using that, we figured out, the cavity's stable or it's not, right? Now we're going to apply the ABCD law to this and figure out, what kind of mode do I have? And the key thing to realize, in a laser, I'll just draw a simple cavity here. You get a distribution, you get a Gaussian mode in there, and it's a mode. And a mode means it's a very stable, reproducible, defined structure. So what happens is, if I take, say, the wave right here, and I let it propagate over there and come back and back to itself, it'll come back and look exactly as it did when it started. So mode is self-reproducing. It's going to be the eigenvalue for this cavity, and it's going to be the distribution of field which keeps reproducing itself as it goes back and forth. It's not morphing. The rays, every ray was different, and maybe after a few hundred passes it comes back to itself. And so the rays kind of rattled around here. Every ray looked different. The mode, the wave is going to follow that shape, come back, and look exactly as it did before. That's the key. So how do we use that? Well, I'm going to find a Q here. That mode, there's a field that's got a Q. I'm going to insist that after one round trip, Q is the same. So what we do in this cavity is say, well, one round trip is defined in terms of this ABCD. So I'm going to say Q must equal AQ plus B over CQ plus D. And now I'm going to solve for Q. And I'm going to get a quadratic equation of Q in terms of A, B, C, D. And I'll separate the real and imaginary parts. And I'll know everything there is to know about that mode. So then I'll start adjusting my cavity to give me what I want. So that's the basic process there. And that's the key idea behind this whole thing. Now let's do an example. So this is the basic idea. You know, just insist on self-reproducing modes. This is now an equation we can solve for Q in terms of ABCD. And so now when I build my cavity, and I'm building the cavity, so I'm choosing all these dimensions, I'm in charge of ABCD. I will choose ABCD to give me what I want. So that's how you as the designer can create the mode, the shape, the focus, all that kind of junk. Let's try a simple example. And let me just motivate it by this way. Typically in the cavity, when I'm designing a laser, I really want to know, let's say I'm right here. I'd like to know what's the spot size, because I want to know what the intensity is and the focus. And so spot size is not given by Q. Spot size is given by 1 over Q. If I have 1 over Q, I've got 1 over the radius curvature and the spot size term. And so that's why I gave you that other equation, 1 over, and so I'm going to do 1 over Q, and I can always never remember this thing. Okay, so 1 over Q. 1 over Q in the cavity is going to be C plus D over Q divided by A plus B over Q. Okay, let's expand that and solve it. And so you get, it's all nuts. All right, I'll do it on the board here. So you expand it. You get A over Q plus B over, I'm doing it wrong. Let's just do it. Okay. 1 over Q equals C plus D over Q divided by A plus B over Q. Okay, multiply both sides by A plus B over Q. And so I get A over Q plus B over Q squared equals C plus D over Q. Okay, write this, put the terms together, you get B over Q squared plus A minus D over Q minus C equals 0. It's a quadratic equation in Q, or in 1 over Q. So what's 1 over Q? So 1 over Q equals minus A minus D over 2B plus or minus the square root of A minus D squared plus 4BC all over 4B squared. Okay, now we can simplify this a bit. Remember that AD minus BC equals 1. That's because I've got this, that's the ABCD rule for the matrix. So 4BC must equal 4AD minus 4. I can plug that in there. And this simplifies. And then I'm also going to remember, what was the stability condition? Remember the stability condition? A plus D over 2 is less than 1. Okay, so when I write this, I'm going to find this is going to be an A plus D over 2 minus 1. This is going to be less than 1. So when I rewrite this and do all the math, it becomes this. It becomes, I'm going to get minus A minus D over 2B plus or minus J times the square root of 1 minus A plus D over 2 squared. And all of this is over B. So, do this substitution here, put it in. Notice that I've got an a plus d over 2, and that's less than 1. So I take the square root of a negative number, so I've reversed it like that. And so now this is my new expression for 1 over q in terms of ABCD in the cavity. This is only true in a cavity because I've got this self-consistent condition. And notice this is 1 over q, and 1 over q equals 1 over r of z minus j lambda over pi omega squared of z. I've got a real part, that must be the radius of curvature. I've got an imaginary part, that must be my spot size. So that's why we like the 1 over q component when we're designing a cavity, because now in this cavity I want to design something, and I want to figure out what's the waste right there. So I'll start my ABCD right there. I get my ABCD, I plug the numbers in. I immediately know what my spot size is. I immediately know what my curvature is, and so forth. So that's why we do that. But remember, keep in mind, this is only true inside the cavity. This will not work outside the cavity. I've insisted that the beam transform into itself after one round trip. Okay, let's try a quick example. Yeah, we got time. Of a very trivial cavity. So I want to do a simple cavity with a simple ABCD, but we want to point out some of the issues we find. So let's say we got a cavity that looks like this. I've got a flat mirror and a curved mirror. So there's my cavity. So r equals infinity, and just call this, I put some numbers in it. I think I did. Let's make this 100 centimeters. And let's have a distance L, and let's make that 20. Okay, I'd like to know what the mode looks like inside this cavity. So I don't know anything right now, just I got to figure out the mode. So I've got to do an ABCD. It doesn't matter where I start it. It'll tell me what the Q is wherever I start. I'm going to start it here, just to be clean. So we'll start there. So I'm going to go L, focus, L, reflect. And so the ABCD this is, first I go 1, 20, 0, 1. Then I focus, 1, 0, minus 2 over 100, 1. I come back, and then I hit the back mirror, which is just unity. So I usually don't put that in. And I compute this matrix. And I do it by hand, and then I mess around for an hour because nothing's working. So then I go to Mathematica, and I do it right away, and I get the right answer, and I scribble out all the wrong answers here. And so this works out to be 0.6, 32, not 8, as I did last night, minus 1 over 50, and 0.6. So there's the ABCD starting right there. Real numbers. Now, what's the radius of curvature of my mode right there? So my radius of curvature, okay, there it is. 1 over r of z is that. So 1 over r of z, 1 over r at that point is equal to a minus d, 0.6 minus 0.6, 0 over b, whatever it is, 32. So 1 over r is 0, r equals infinity. So I've got a plane wave right here. So it turns out my field is planar right there. Interesting. So is it what else can you tell me then if it's planar? What part of a Gaussian mode has a plane wave? Z equals 0, or the waist. So the waist must be right here. That must be the waist, because I got a plane wave right there. So how big is it? Okay, well, plug my numbers in. I know that lambda over pi omega, we're at the waist, so it's going to be omega naught squared, must equal all that junk up there. And it's going to be 1 minus a plus d over 2 squared, square root of that, divided by b. So I want to get omega naught. So omega naught is going to be the square root of all this junk. So I'm going to have I'm going to put that up there. So I'm going to get a pi over a lambda over pi to the 1/2, and then a b over the square root of 1 plus 1 minus a plus d over 2 squared, and the square root of all this junk. So that'll give me my omega naught. Now, I wrote it down just painfully, but I want to give you a heads up. The formula gives us all this stuff here. When I take a square root, sometimes when you do a computation, you get a negative value for b. And then you go and you plug it in your calculator or whatever, and it comes up. Can't do it, or something stuff like that, because you're taking a negative square root. So I always, when I compute this thing, if I write general formulas, I'll usually take the absolute value of b. Just if I just want to create a general formula I'm going to call on later, take the abs of b, and then it'll work out. Then no matter what the sign is, you're safe. Sometimes it comes up negative. All right, so how big is it? Okay, let's say the wavelength is 1 micron. So you need the wavelength. So I've got 10 to the minus 4 centimeters divided by pi. So I'm doing everything in centimeters. And then square root of, what was b? So b was 32 divided by 1 minus 0.6 plus 0.6 over 2 is 0.6 squared, so 0.6 squared. Okay, so this, you can plug the number. This turns out to be 0.64, so that's 0.8, so that it all works out. Anyway, you get done with this, and you get a number. I got 0.035 centimeters. So 0.3 millimeters. Pretty small spot. That's fairly typical at a waist. So 350 microns. So that's how big the beam is right there. Not very big. So I now know, my omega naught is 350 microns, and I know where it is. Now I know everything else about the beam. So what's the beam look like on the other mirror? So it's going to spread, of course, and do its thing. And we can do a lot of things here. I could just say, okay, let's compute a new ABCD right here and compute it. Or I know Q here, I could just add 20 and compute the new Q here. I've got to invert everything. Or I could say, well, I'm just curious, what's the size and the radius of curvature? So why don't we just use the formulas we've got? And so let's look at the radius of curvature of the mode here. I know it's flat here, so what is it there? So what's R at 20? And that's equal to, remember the formula, Z times 1 plus Z naught over Z squared. So I've got to compute Z naught. Z naught, remember, was pi omega naught squared over lambda. I can either plug the number in if I want, that works, or I can write Z naught in terms of b over the square root of stuff. You can do either way. I got, doing it, I got Z naught? What do I get for Z naught? I got Z naught was 40. 40 centimeters. Okay, so what's the radius of curvature here? So it's going to be 20 times 1 plus 40 over 20 squared. So 1 plus 2 squared is 4, plus 1 is 5, times 20 equals 100 centimeters. Notice, what's the radius curvature of the mirror? 100 centimeters. So when I've got waves hitting a mirror and bouncing back, the wavefronts match the mirror. So here I'm coming in, I hit a flat mirror, and I'm bouncing back, my wavefront's flat. Here, I'm hitting a curved mirror, and I'm bouncing back, the wavefront matches. So my radius of curvature here match, radius of curvature here matches. So when I'm in and I want to stress, this is only when it's a retroreflection. Wave comes in, leaves, it matches the curvature. I could make this cavity look like this. So I could put a 45-degree mirror here, and then this curved one here. And if this distance is 10 and 10, so I go 20 centimeters from here to here, I'll find I have a flat field here. I've got a radius of curvature of 100 here. I don't know what it is there. This is somewhere in between. This is not a retroreflection. This is just a redirection. So if the mirror, if it hits and goes off at another angle, the wavefronts do not match the curvature. But if it's a conjugate reflection, if e to the plus j becomes e to the minus j, minus z, whatever, then the wavefronts match. And then you can go through and calculate the spot size. That's pretty easy to do. I got the spot size here was 398 microns. Here's 350. So this is another lesson we learned about laser beams. They're pretty small. This is a mode now. This is the mode, and it's pretty small. Now that's smaller than a pencil lead. That's a tiny little beam, and it's going back and forth in here. But it's the size. You know, if I put a small beam here, it's going to spread, and it's spreading just enough so that it's got a radius of curvature 100, which matches that. So when it reflects back, it comes back to itself. So the size has adjusted itself to be exactly so it matches this cavity just right. If I move this mirror, I'll find the spot size changes a bit and all that kind of stuff, but it's all going to be self-consistent. So all of that came out of the ABCD. So that's a very that's why I love this law, because once you've got ABCD, you are in total control. You know, I can adjust my cavity to change the spot size to be what I want it. I can adjust the curvatures. I choose the mirrors. Now I can make the beam be what I want it to be. So that's how it works. So any quick questions about that? Okay, so this is going to be the design tool for your laser. So now that you know this, now we'll start learning about stimulated emission and all the gain stuff. But now you know enough to put a cavity together. And that's the design. Okay, we'll stop there. So are we overdue? I don't know, whatever.